Cool.
There we go. Ghost.
Good time.
All right.
So,
I started the recording. Hello, everyone. Welcome to the Game Development Club. I'm going to quickly make this full screen, and I'm going to put this over here. My name is Josh, and today we are joined by Alex Williams, and he's going to be talking about a custom render pipeline he's been working on. So, Alex, I'm going to give the floor over to you, and why don't you take it away?
thank you. So, yes, so I was practicing this ahead of time, and I noticed I was spending a lot of time on very small details that went nowhere. So, forgive me if I speed through things a little bit, and feel free to slow me down if there are any questions or anything just does not make sense at all, because that could just very well happen. So, some background info. I started this in about early 2020, like right before the pandemic hit. I wanted to learn a little bit about graphics programming and kind of use a real project to kind of organize the learning around. And at the time, I was really into the look of the game Return to the Obra Dinn, which is like I have some pictures of it later on, but basically it's like a 1-bit render process where you have a 3D game in 3D world space, except the output of the image is always just going to be one of two colors. And he used a bunch of visual techniques to kind of still make it look like something you could actually walk through and step through and keep track of where you are. And also, probably most importantly, the developer documented his entire render process, which helped helped a lot. And also, I apologize ahead of time if anything just does not have any sort of artistic value. Unfortunately, that's not something I've ever been very good at. So anyway, moving on. Return to the Obra Dinn. This is what it looks like in gameplay. As you can see, it's just one of two colors, black or white. And pretty much everything about the render process is designed to make it so that you can still have a sense of depth and awareness in the game world. And it was meant to evoke very early Macintosh games. And internally, behind the scenes, what happens is everything is graded on an 8-bit monochrome scale, which means that everything is one of 256 colors. And things like lighting and shadows and textures all contribute to that. And then at the very end of the render process, he just clamps it down to one of two colors, black or white, and just outputs it like that. So it has that classic look while being able to do more complicated stuff behind the scenes. And he also used some encoding practices to put extra data into each kind of frame. Background info number 2 is the Game Boy Color. I had one of these. I'm presumably pretty well known. And I kind of, since it was, that nostalgic value, I was like, okay, well, this is something that I'm familiar with because I was one of those jerks who just played it all day. So, why not just try to do something like similar but with Game Boy Color? Because they had 2-bit coloring, which is instead of having just a monochromatic on or off, black or white, it could have different shades of gray or shades of green. And if you played an original Game Boy game on a Game Boy Color, then it could swap out those color palettes on the fly. So instead of having like a green monochrome, it could be like yellowish brown or something. I don't know. It depends on what kind of game you played. And there were 4 different layers, so in a way, it was technically more like 16 colors. But that's just a little thing. So those kind of formulated my goal. Learned from Lucas Pope's dev blogs and tried to do a similar approach with 2-bit color patterns. And in the process of doing so, kind of understand what the whole deal is with shader programming and graphics programming. So going to start off with the scriptable render pipeline. As a brief overview, when you start off a project in Unity, it might be different nowadays, but at the time that I started the project, it would just start off with a built-in render pipeline that you'll typically see. The data is stuck in a very fixed format of float values, which is like how the computer considers real numbers, so like decimals and things like that. and everything is kind of set to follow a strict API. So let's say you wanted to do some sort of post-processing, there'd be a specific area where you put that stuff in, but it doesn't necessarily, like, you don't have direct control over it. You just say, I want this to happen. Can you fit this in here? And then Unity will say, cool, yep, I'll do it. Let's do it. And go from there. So that's where Unity's scriptable render pipeline kind of has its strengths, in that you have the power to just completely change that stuff around and decide where it goes. You can control it. So instead of using like real numbers to represent the colors, you can just use integers, which is what I did, and comes into play very well with the encoding process. Bad downside is that it's got a much stricter learning curve. I still don't really understand it all that much, and a lot of basic features need to be re-implemented. I used this tutorial from Cat-like Coding, or I used a tutorial from Cat-like Coding to do a lot of the work. And so if you need to check it out, please check out the PowerPoint, which I'll hopefully upload to the Discord. So these were the specifications I tried to work with. Data format, use 32 bits per every pixel, which is basically like, technical wise, you'll have 4 different, you'll have a red channel, a green channel, a blue channel, and an alpha channel, which handles transparency of the objects on the screen. And they all kind of combine to create the final color that you see on the screen. So there'd be 32 bits, basically meaning that each of those 4 colors can go from 0 to 255. There's 256 values that it can be. I also added multiple render targets. A render target is basically kind of like the screen behind the scenes. So like, let's say you want to render out the background geometry of the game world, like static data. You can render that to one screen, and then you can render like things like enemies or projectiles or the player character onto like another screen, and then you can combine them at the end. And that kind of frees you up to do like extra stuff that only applies to like one of those things. So let's say you want to do some sort of like smart motion blur. You can have the motion blur apply to the character and the enemies, like that whole render target, but not to the background. And then when you combine them, it'll be like the background will still look crisp and clear, but the player or the enemies or whatever's on the other render target will look all different and in motion. So it's a way to kind of do more sophisticated stuff at the cost of taking a little bit more. It takes a little bit more data and more effort to do. I wanted to add in post-processing. There's currently no lighting data. I was like, you know what? Screw it. I don't want to deal with this right now. And then also the ability to scale the resolution around, which is kind of small but important for preserving 2D, Game Boy pixelation. So starting off with the initial scene data, this is the process from start to finish, like the input to the output. And actually, you know what? Before I do that, I want to hop into Unity and show what the final output should be. Okay, good. I was losing connection about an hour ago, so I'm glad to see that I have not disconnected. So this is kind of what part of the input looks like. This is just a test scene that I put together, which is why nothing really looks like it belongs. This is all just stuff that I just threw out to test stuff. This is what the input looks like. And then here's how the camera processes it. But then when you hit play, everything kind of combines together to create this more pixelated kind of graphic approach. You can swap out the different colors and things like that. So this is the final result in its current form. And with that in mind, I'll hop back into slides and kind of go through start to finish, how did it get to that point. So the initial scene data is all of like the 3D meshes and models and their textures, positions in the world, things like that. All of that kind of gets combined and squeezed down into the data that gets sent to the graphics processor. And let's see, as far as my own pipeline goes, it's all pretty standard stuff. It all gets passed into the graphics, and then depending on what your what material you assign to each object and what shaders you have running behind the scenes, they can use the input data in specific ways. Like you have complete control over what's going on. So, it's cool because again, you can customize it how you want, but depending on how you want it to look at the end, what would look fine in a normal game might look just absolutely terrible in a custom pipeline like what I got. So starting it off, the primary data pass, which is also what I call the encoding pass, takes in all of the scene's input data and tries to create like an intermediate format that kind of just organizes everything for the final run through. So this is like phase 1 of 2, if you will. So the shader directly kind of is directly written with like the buffer in mind. The vertex data, which is like the shape of the mesh, is processed completely verbatim, pretty much. Like if I passed in the model of a hand in, I'd get the exact same hand out. Like the shape just doesn't change. So that's like step 1 of this encoding pass. And then step 2 would be the texture part. So it takes all of the colors and textures of everything and outputs them properly. So the main thing that I wanted to do to kind of emulate Lucas Pope's design is that he squeezed a bunch of data into into each color channel, even though it shouldn't really have been there. So he did stuff like the red channel, say, would have all of the lighting, would have all of the texture data of like the black and white stuff you see on screen. And then he would take the green channel, the blue channel, and like the alpha channel, and just put like whatever he wanted to into it. Like he would put in lighting information, like outline data. He did some really crazy stuff, which all helped him create the final image. So I kind of thought, even though, as you see later on, it wasn't really necessary that I do this, I still felt it would be cool to kind of learn that anyway. So it truncates the textures a bit. If you're this, I don't know. I feel like this is kind of hard to explain pretty well, so I put the information in here, but I'm kind of going to slide through it relatively quickly, so as not to lose too many people. So this is just a quick look of how everything looks when you first pass it in, of like the texture data and all that sort of thing. And then this is what it turns into. It looks a little bit garbled, as you can probably imagine. Like a bunch of these colors just change completely. And then this gradient turns into like 4 mini gradients. And part of that is because of the encoding. Again, this is just kind of more math stuff, so that if you're doing programming, it can kind of be an example to illustrate what's specifically happening behind the scenes. But basically, it's moving stuff around so that part of the green channel gets squeezed to fit into the red channel, part of the blue channel gets squeezed to fit in here, and then it leaves you with extra space to store stuff like depth, which is what this is all blank, but I put stuff like depth in here so that I didn't need to put it in other stuff. So it saves a bit of data, not really a whole lot, but it could be useful if that's all you need to get things going. And after that, it moves on to the post-processing stage. So this is kind of what happens after everything's been rendered. Like all the 3D mesh data has been organized into like a 2D kind of image of sorts. Post-processing, I imagine is probably pretty familiar to a lot of people listening, but it just takes that and it transforms it into the final output image. It's common in both game development and video editing, rendering, stuff like that. I noticed it was used. Well, I didn't notice it was used, but apparently it is used in the movie Knives Out, if anybody's seen that, to kind of emulate classic film details, even though the entire movie was filmed in digital. So it did stuff like running an algorithm to add these like little outlines to the lighting information, which is very bizarre. I have no idea how that was programmed, but it was all done algorithmically. And then games are very similar, but the main difference is that Whereas film works with something like, just a 2D image or whatever. Games can kind of store as much of the 3D stuff as they want to. So like if you want to store the depth of an object and save it for later, you can kind of do that. And it wouldn't really make much sense if you just put it out as an image. But by storing it inside the data behind the scenes, you can pull stuff out afterwards and create more interesting visual effects as a result of that. So that was kind of the approach that I took as far as the post-processing goes, is just store a bunch of stuff behind the scenes. It'll look like complete garbage. Like this is what it looks like, and then afterwards decode it all and then print it out onto the screen. So let's see. So first of all, it goes back into this data buffer. I'm going to back a couple screens. It goes back and pretty much reverts from this back into this. Some bits of color information are lost in the process, but again, it's just something that I wanted to do. And then afterwards, it kind of uses each of those channel data as a way to pinpoint exactly what color it should use. So I kind of imagine it like a Cartesian grid, where you have a value from like 0 to 1. And then if it's greater than 0.5, like say the red channel is greater than 0.5, and then you'll end up in like this half, and then you use the Y channel, or the green channel, I'm sorry, to figure out which of these colors to use. So that's kind of the way I think of it. Hopefully, I really hope that makes sense. Again, feel free to stop me if you have any questions. But yeah, it's just imagine it as like a value of 0 to 1. And depending on what those are, they'll serve as coordinates to give you your final color. And one other thing that kind of added in later on was the ability to transition between each color naturally. So if you look on this just 2D grid, you'll see green can go to white, and there's this band that separates them, and it's there for most of the colors. But you can't go to something like black to white naturally, or green to red naturally. It's kind of weird the way it works. So I kind of used the blue channel to facilitate that and almost turn it into like a 3D cube of sorts, so that if the blue channel is greater than 0.5, say, it will flip the grid pretty much and just invert it. So green becomes red, black becomes white, so on and so forth. So that kind of gives a way to smoothly transition from each color to the other. So it does take up more data though, but I consider it to be worth it enough. So this is what it looks like before rendering, and just taking the stuff that's been described so far, this is what it looks like after rendering, and it's not great. It looks pretty bad. It's like there's no sense of depth, no sense of texture. Everything is just very sudden and instantaneous, and that's because of the very limited color palette and not really doing anything to kind of massage the output ahead of time to prepare for that. So both the solution that Lucas Pope did and that I used was to have a dither pattern. So basically, you can see dither a lot. It was used a lot back in like old games, like say the 90s or whatever, when they had very limited color palettes, just because there was so little data that was available on the cartridge or the game or whatever, that they kind of had to make do with very few colors. They would use this approach to kind of blend between the two more naturally. So it basically, you have like this checkerboard pattern, and each one is a unique value from say 0 to like 256. That's the value that I used for my dither pattern. And so it's like it uses an algorithm to strategically place each of the values as to create as like precisely uniform, or I don't know the right word for it, so I apologize for that. But it just creates this pattern to make the transition as smooth as possible. And then it will take this pixel and assign it to a pixel on your monitor. So like, just imagine this as much bigger, and much higher resolution. And that's kind of how the dither pattern is used both in this render pipeline along with Return of the Obra Dinn. So here's just an example of it, of how it's used within my own color space. You take the pixel, so let's say it's 0.45, and instead of just using a hard 0.5 thing, 0.5 border for each of them, you adjust it. So now suddenly it's much more likely that you'll end up in the red color than anything else. So this gets done differently for every single pixel on the screen. So like this has a very low lightness, so that'll cause it to be like much more likely to be red, and so on and so forth. So it's not something that seems like it would work, but afterwards it actually does help out a lot. Like this still isn't like super best quality thing ever, but I mean it's much easier to make out than what it looked like before, which was just like flat colors, no depth, no texture, nothing. And it's much closer to the gradients that you'll see, that you are supposed to see in the input. So let's see. So Obra Dinn applied this. However, what Lucas Pope realized was that just using a static 2D buffer to like overlay as a rectangle in front of your screen, kind of like just like a screen door or whatever, led to problems because as you move the camera around, those pixels aren't going to stick to the surface of the object. So there's going to be a lot of like blinking in and out of pixels and a lot of like weird movement. And he calls it a swimming effect. And it leads to a lot of motion sickness. And it's really not great. So his solution was to map the dither onto the inside of a unit sphere. So a very similar way to how skyboxes are rendered. You just have like a little sphere, follow the camera around, like stay perfectly in sync with the camera's movement, and then it like renders the inside of the sphere to be perfectly like in the background. So that way it's the kind of solution where as the player looks around, you'll see different parts of the unit sphere, but as you move around like forward and backward, left to right, the sphere will move with you. So the texels, just short for texture pixel, will stay unchanged, and you'll kind of see like the same space over and over again. So again, same concept as skyboxes, and it worked really, really well for Return of the Obra Dinn. Now, in my case, there was a key difference in the camera that meant that I was having a lot more trouble doing the same solution, which is that my camera is in third person. So, I mean, again, this is very, very basic information if you're familiar with this stuff, but when you have a first-person camera, the camera, like the fulcrum of rotation is the player and the camera itself. So as you move up and down, like the camera itself isn't changing position, it changes rotation. But with a third-person camera, you're changing both at the same time. So you want to move the camera left or right, the camera is going to move with it because the player has to stay in as the center of the view. So that causes problems with the unit sphere, I'm sorry, because the pivot is not the same place, like the sphere's pivot is not the same place as the camera's pivot. So it leads to even more swimming in some cases where the pixels just aren't matching up properly. And also there was also the problem that I couldn't really figure out how to get it to map to a unit sphere. That's a story for another day. Whatever. So I kind of took one of his earlier prototypes and adapted it in my case, which is to take the 2D mesh, like the screen door effect pretty much, and then have it move with the camera rotation. And that's what he used in the early stage. He eventually moved on past it because the unit sphere worked much better with 3D space. Unfortunately, I didn't really have that same luxury. But you basically scale the dither to the camera resolution, so every pixel maintains that kind of 1-to-1 ratio with the screen background, and then as you rotate the camera, you kind of move the dither pattern along. So let's see. I'm going to see if I can illustrate it. This might not be the best idea. You know what? I might. Yeah, no, this is a bad idea. I'm just going to go back to this. Ignore that. Cut it from the footage. Oh, there's a video example on the very next slide. Okay, I'm a genius. All right. So it works well, but as you move away from as like an object is further away from the camera, it won't work as well because it'll move at a different rate than the stuff that's closer. We'll just play the video so you can see it directly. The stuff in the background, if you pay attention, it's going to be moving much differently than something closer to you. So what works in the background might not work in the foreground, and so on and so forth. So my solution was to encode depth for each object, and then in post-processing, use that to kind of affect how fast the dither rotates with the camera. It's not a perfect solution. There's a lot of problems with it, and I'm going to get some more of them in the future. But really, I can live with it. At this point, I was like working on trying to do the 3D stuff for like 3 or 4 months. Whatever. I'll live with it. That was my logic. So another main problem with the way I approached it is that the offset angle does not account for the camera's pitch. So like as you change your view to look down or to look up, it's not going to affect how the dither rotates, like speed-wise, which is a problem because as you have the camera at an extreme pitch, rotating is going to move the dither at a different rate. So again, I'll just hop into the demo and try to demonstrate it manually. These big cubes, pillars, are moving, like they're just swiveling around in this one circle. Meanwhile, the dither is just going entirely along the background. It might just going to change the color palette real quick. It's just kind of continuing as if it's perfectly horizontal and moving along from there. So that's another big problem with it, and just kind of breaks the connection, breaks any real illusion. So you could try to account for this. However, trying to do it in an equation doesn't really work great either, because as you change the pitch, the pixels in your dither will also end up moving horizontally to adjust for the change in speed, which I might not be explaining that the best, but it causes the pixels to move in ways that they shouldn't. So that also breaks the illusion. And since I was just so done with it after 3 months, I just, again, cut the losses. I'll deal with it. One good solution might be to limit the pitch so you can only look down this much. It's still not great, but it helps reduce it a little bit. And one other problem that I don't think is in the slides, but I want to mention anyway, is that the stabilization of the dither is also much closer at the center of the screen than at the 4 corners. Because again, 4 corners are extremely close in terms of depth, and it just doesn't map on as well as, say, towards the center of the screen. And then resolution downscaling, you've been able to see this just throughout. It's a way of changing the resolution dynamically by just dividing the overall size of the frame buffer as needed. So, I mean, it wouldn't really be, like I say here, wouldn't really be an actual Game Boy homage if you knew what you were looking at. So that's kind of why I went for it. Just do that sort of rescale. Bad news is that the lower the resolution gets, motion sickness gets worse, and absolutely worse. I limited it beyond what the video example here shows. I'm just going to skip past it because I kind of just went through it anyway. So there we go. Next up is color palettes. I'm sorry if I'm taking too much time. I'll try to hurry it up. Color palettes is basically what you can see in here. Change the color, it'll swap over to a new one. Main goal with that was to kind of have the color on as like a little thing in the background that can be accessed at any time, so that instead of the pixels trying to map themselves to the color, they'll map themselves to that Cartesian grid that I had going on a few slides back. And then after everything is taken care of, just say, okay, replace the green with purple, replace the red with, I don't know, blue, something like that. So it's just a way to effectively replace the colors at runtime however you need it to be done. And this is kind of like the main color part of the Game Boy Color. So let's see. Yeah, they're all stored as JSON files, read in through a static method. This is more programming stuff, which might not be relevant at all. So if you need to check it out, you can look at this slide afterwards. I did write a Python GUI to demo the palettes on images. It kind of sucks. Just gonna give you a heads up. I think I ended up sharing that with maybe somewhere. It's somewhere out in the internet. So I wouldn't recommend using it, but it exists. For assigning new color palettes, there's just a single mono behavior which runs in the background and takes the color palettes and just assigns them as needed. I really just did it to get it done. It's not really sophisticated or elegant at all, and it should not, I don't know, maybe it'll stick around. Who knows? Not me. I don't know anything. But, it's just a way to kind of hook things together. Controller gets assigned to a game object, not a GameStop. And then it changes the palette from there. And there's a little bit more to it than this, but I'll get to that in a slide or two, because right now is motion sickness. So again, prevailing theme throughout this is that if you're prone to motion sickness, or even if you're not prone to motion sickness, you'll get sick pretty quickly. And there's a lot of flaws with using the approach, especially considering that even with all my attempts to stabilize the pixels, it's still not perfect. So a good solution would just be to preserve the pixelated style. Yes. A good solution would be to preserve the style while easing the overall experience. Or you could just remove the whole dither process. I didn't care at this point. Again, you can kind of sense the theme of losing my sanity. So this is one way to do it. Unfortunately, it's not the best. I would like to refine it if given the opportunity, but it's something, and thankfully it doesn't have motion sickness, even though it does not look great, and all that sort of thing. Not to say it looks great like this, but again, stuff to consider going forward. And then another accessibility issue is color blindness. If you have trouble differentiating the colors, then even if you might not even be able to tell what's going on, even more so than how it is right now. So how can you kind of approach it so that somebody who has some sort of color blindness, one of the types of color blindness, can still play it comfortably and kind of differentiate the different colors. So you could create separate palettes that replace any problematic ones. You could also modify the palettes in real time so that if there's two colors that would blend, that stand out for trichromatic vision, but then if you have some form of color blindness that blend in together, you can kind of identify that and separate them out so that they look different to a colorblind user. So I wanted to start with the second option since it's more programmatic. Introduction to the types of color blindness. This is very limited because, again, this is only, you can't really fit an entire thing like this into one slide, but I'm going to do my best anyway. There's anomalous trichromacy, which is you can still see, you have 3 functional color receptors, but the problem is that differentiating between some of them can be more difficult. So that can lead to a case where it's harder to pick out red colors, it's harder to pick out green colors, stuff like that. Then there's dichromacy. Yes, dichromacy, pronounced that right, where you can only really, one of your 3 color receptors is not really working right. There's protanopia, where you're lacking red photoreceptors. Deuteranopia. I mostly read this stuff, so forgive me if I get the pronunciations wrong, where it's the same thing, similar with green photoreceptors. And then tritanopia, which is blue photoreceptors. So there's a simulation website here that you can use. One thing you'll notice is that both red blind and green blind both have some similarities, but as opposed, just they're not the same, of course, but like in comparison to blue blindness, it's going to look very different. So that's kind of the approach. There we go. Sorry about that. And then there's, of course, monochromacy, which means you can't see the color at all. So I think step one of just debugging and testing solutions would be to simulate color blindness, which is a little bit more difficult than it would seem at first, because computers use the RGB color space, whereas the human eye has all these different cones and rods and what have you. So it's kind of perceived differently and hard to map one onto the other. So although there is a color space called LMS, which approximates it as best as it can. So it kind of organizes things based off of wavelengths and the types of the wavelengths that are most susceptible to the different types of cones. So really the process for properly simulating color blindness would be to take the RGB color, map it onto LMS space, change it around to fit the color to kind of adapt for what a colorblind person might see, and map back into RGB. This should say RGB. Ignore that. And it's annoying because you kind of have to use matrix multiplication to do all this stuff, which C# does not support in the mono compiler. So yeah, it kind of sucks. But thankfully, there were a lot of algorithms and matrices available online that I was able to use to ease the whole process of converting it to LMS and modifying for color blindness. That's that whole approach. And I just had to implement matrix multiplication on the side very poorly. And then modifying the palettes for color blindness. So this is what I was kind of alluding to earlier, a few slides back, where you want to make the colors more recognizable to a colorblind user. So you just kind of nudge them a little bit to a more distinct color. My approach, as will be shown on, I think, the next slide, it doesn't work at all. It's really bad. It's awful. You shouldn't use my specific implementation. There are a couple of research papers that seemed to do much better, but they didn't have their code available and I couldn't use it. So, really consider this to be a warning and just a first step. So the best way to kind of approach modifying the color for a colorblind user is to adapt it to the CIE lab color space, also known as lab. L for lightness, A is kind of like a scale between the red and green colors, and then B as a scale between yellow and blue. So the more negative B gets, the more blue it gets, whereas the more positive it is, the more yellow it gets. And the same with A, and lightness is fairly self-explanatory. So if you want to say modify something for tritanopia to adapt for the lack of blue photoreceptors, again, nomenclature, I'm not great with the vocabulary, so I apologize. But you kind of move the L and A around so that they adapt more to what the B is. Having a blue color will darken the overall image and make it less red and more green, whereas the opposite will happen if it's positive. Then you convert back to RGB and use that. Similar approach for the other two, except instead of modifying the L and A, you modify L and B and use the A as your point of reference. And then you use different constants. Again, the result sucks, doesn't work. At least mine doesn't work. Like here's here's an example of an image that would look very confusing, not great to somebody with protanopia. You can kind of see like a fade in between blue and purple. which just kind of gets lost completely in here. This is what it looks like after I tried to modify it. So, great job. It looks awful, and it works better with some of the color palettes, but really it's just not consistent enough in my own implementation. So it's just going to have to be something to refine in the future, or just replace the color palettes. So again, next steps. This is kind of the conclusion. Thank God. I'm sorry for anybody who had to go through all that. So the next steps would be, actually implementing the multiple color layers. I mentioned at the start that the Game Boy Color was able to do like a background color layer, which had its own set of 4 colors, as well as something like a user interface layer, which could have its own set of colors, and then like objects that move around on the screen. I don't have that in my own pipeline. There are a couple of ideas I described here, but none of them really have been implemented. I didn't do any of them. They're just ideas. Replace any globals. Again, global variables are never a great idea, so it'd be cool to get rid of them. Improve the dither offset, considering how many hours I spent talking about that. That would probably be good to improve. Refactor code to kind of bring what I learned back to like the starting stuff. That's kind of the consequence of learning as you go. Remake the Python tool in Unity so that anybody can save their own palettes with it in the actual game editor, and you don't have to open up a separate program. Write a Photoshop plugin so that if an artist is, say, making a texture, they can preview it before they export it and put it into Unity. Make it not suck. That would be cool too. And in conclusion, it's not really finished, but I do have some demos and a survey if you want to take it. Any question? Is anybody still alive?
Yeah, everybody's still here. Everybody usually we're silent throughout. No, it was really good. This is the part where everybody unmutes their mics. We all clap together.
Hello?
It was fantastic. It was really good. It was really informative, really well thought out. What's up? Sorry? Alex?
I don't think you can hear us.
I don't think you can hear us. Hold on, we might have to clap again.
Oh.
Hello? Alex?
Hello.
Hi.
I'm sorry.
All right, we have to do it again. Everybody unmute your mics again and clap again because you couldn't hear us.
That was a bad time for my audio to cut out everybody else's microphone.
Yeah, no, it was great. It was fantastic. It was a really good presentation, really well thought out. I think everybody was here and listening. 1 or 2 people actually messaged me like, wow, this is really interesting. It was a really fantastic job. I'm going to open the floor to questions. I'll continue the recording if everybody's okay with that. But yeah, if anybody has any questions, feel free to jump in and ask away.
Also, sorry, I'm not sharing my screen anymore.
That's all right. If you want to share your screen again and just open up the demo, I think that would be pretty cool.
Oh yeah. Right. Hopefully it works.
Yeah, there it is.
So there's a couple.
Gold Requiem, nice. That's good.
I just named them as to whatever, Let's see. Letters. Yada yada yada.
Don't you have one that's called like Stone Ocean as well?
I don't think so.
Oh, okay.
There's this one for part 4.
Oh yeah, nice.
I abbreviated it because but yeah.
Yeah.
Might be something stone related. But yeah. No other questions. That's cool.
Yeah, that was really, really informative.
Yeah, I hope it helps at least a little bit, because graphics programming is super nebulous and it's hard to follow. Oh, there is this last slide if you want further resources with links. This is the textbook that I used for almost all of it. I don't know why they used this as the book cover because that's clearly not rendered in real time. But let's see. I mean, actually, well, they might have. I don't know what theater tech is like, but see, so yeah, that's the textbook I used for a lot of it. All this other stuff. I did not add the stuff for the color blindness accessibility papers, which I should add. They're linked here, but again, sorry, you're gonna have to search for them. I should download this. I'll just get a link.
Yeah, if you send it to me, I'll post it in the. I shall post it in the server. That way, anybody can see it. I'm going to go ahead and end the recording. Thank you for everybody who's watching on YouTube. We generally meet every Friday from 2 to 4 p.m. Tomorrow, Saturday the 17th, we're going to have another meeting where Christian Oak is going to talk about VR. So, yeah, thank you for watching.